yes, how to make AI faster, smaller, cheaper, greener. So I guess the answer is quite simple, and the solution is simply to optimize AI energy consumption. But why energy? I think we can even tackle an even more important question: what drives the world? So it sounds like a big question, and to answer this question, you might think, of course, about money drives the world, love, or whatever. But I think I always recall about one thing, one book that my father was telling me a lot about it, which are these books, which basically says that energy drives the world. And here energy is really like the physical quantity, the energy that actually has a lot of impact on a lot of things that happened in the real world. So indeed, basically the capacity to find and deploy energy at the right place has had a huge impact in the history. And this is actually well documented. You can think of Middle East wars, nuclear history, or a lot of other things. And the idea is that this has had impact on, economy, national security, or even, outbreak of wars. One thing which is important is that humans are closely related to energy, so which means that if you are French, you might know Jean-Marc Jancovici, who says many people may mean a lot of energy consumed, but also the opposites, that a lot of energy, available energy, allows to sustain a lot of people. So this is normal because we have human body, we need energy to think, exercise, and also a lot of machines to support us. And this is actually also reflects in data. So if you look at the 70 last years, you can see that the energy consumptions have grown a lot. And actually, you can see that it led to even a higher population in the 70 last years, but also a higher energy consumption per inhabitant. So now you can actually ask the same questions about AI. What drives AI? And again, energy is at the heart of the progress of AI. So the capacity, again, to utilize energy has been also central is the latest breakthrough in AI progress. And you can think, for example, of transformers. That is actually an architecture that allows to utilize a lot of energy at the same time. You can think of DeepSeek with efficient kernels that allows to have efficient training with very cheap training overall. Or simply about NVIDIA GPUs that consume more and more power generation after generation. It's important to know also that AI consumption is very large right now already with 600 terabytes per year, which is approximately 1.3 times the electricity consumption of France, and will be over 1,000 terabytes in the coming 5 years. So in the end, you can adapt the previous sentence and say that many AI models may mean a lot of energy consumed, but also the opposite. That a lot of energy, available energy, allows to sustain a lot of AI models. And again, this is normal because we need energy to run the AI and also support all the infrastructure around the AI models. And we can check the data, and again, the data shows that in the last 5-7 years, the energy consumptions have grown a lot. And this led to having more and more AI models, but also having higher energy consumptions per AI model. So if you look at state-of-the-art models, now they consume more and more energy, each of them. But now, how does energy drive AI? So energy first powers AI in the main way. So basically, energy is used to run instructions. So you can think of linear layers, attention, non-linearities, and so on. So basically, it takes an input, which is text, image, video, and then you put it through the model, and it does a lot of instructions, which are matrix multiplication, nonlinear instructions, and so on, and then give an output that could be, again, text, image, or video. And this model runs with some specific language on some specific hardware. On this, with all of these instructions, usually there are some instructions that consume more energy, and the ones that you need to know are probably linear layers that usually consume 80 to 95% of the energy consumptions in latest models. But now how energy consumes energy. So basically there are two things, two ways that how instructions consume energy. It's basically in memory movement or computation on the GPU. So on the GPU you have like a memory part, let's say, and a GPU and a compute part. And if you think of like matrix multiplication, what you have to do is first load some matrices, put them on the compute part, so move them, and then perform the compute. And each of these things needs a lot of energy. Not only the compute part, but also the memory movement. A last thing which is important is that there are two phases, also the important phases. There is the training and the inference. Usually we talk a lot about the training, but actually inference consumes in a daily volume like the most energy, like usually 80 to 90% of the energy consumption. So now the question is, how does running all these instructions improve AI, kind of? So basically, energy helps quality. So there are like well-studied, papers on this and on the so-called scaling laws that shows that when you invest more energy at training time or at inference time, then you get better quality for your models. And you can see, for example, on the left, the training scaling laws, where you have like models, state-of-the-art models year after year on the x-axis. And on the y-axis, it's a bit small, but you can actually, it shows how many flops, so how much compute you need to run the AI model. And the y-axis in the log scale. So it means that basically it's exponentially growing how much energy you need to invest during training time to get the best AI models. And you can actually see also the same kind of scaling laws, but for the inference phase, for the testing scaling laws. And in this case, you can see actually that when you invest more compute during inference, for example, you can think of reasoning models when you just reuse the output of the model and make it think about its generation, you can actually reduce the errors on the y-axis. So x-axis is again, how much compute you spend, and if you spend more compute, you can reduce the errors that your models will do. So the main takeaway here is that if you use energy appropriately, because of course you can just waste energy, you can actually enhance the AI quality. But energy has also other impacts on AI output, and actually it impacts the overall performance of the models. So performance is more than simply the quality, it's actually the combination of quality and the efficiency. And for example, if you spend more energy on your models, what you might get is actually more running time because you just make your model run longer. You might actually just use more energy to run your model on larger hardware. You might just spend more compute because energy has a cost. Or you can see also that it has a negative environmental impact because you have to cool a lot of infrastructure to make it work. But something I want to highlight is that even if you don't care at all about sustainability, you should optimize for energy that consumes your AI models because it impacts your model performance. And this has been like a very personal, motivations to create Pruna, basically to align sustainability with, performance of the model without having people even to think about it. They have to optimize it because it just makes the model way better. Now let's take like a concrete example. And for example, we can take the example of the flux context model, which does image editing. So you give an image on the left, and you can ask the model, OK, I want to turn the car in red, and it will do it. And by default, if you take as is the flux context model as shown on Hugging Face, it will take 14.4 seconds on the H100, which is kind of a big GPU. On one side, for example, we have customers that run like this model like 100,000 times a day, which represent 280 kilowatt hour per day. So of course, you might not know exactly how much energy it represents. So I was thinking a bit about like what could be a good analogy. And I like a lot running, maybe like a lot of people here. So I checked like my last race on Strava. And actually, I was doing like a half marathon in 1 hour and 20 at 4 100 watt power. And so this means that to generate all these 100 images, I should have run 510 half marathons. So it's a lot of energy. So imagine yourself, after just doing some run, it's extremely exhausting. I can promise you that, you don't want to do it. And especially it's just for a single customer, right? A single day. So to improve this ratio, I guess I have two options. I can improve my half marathon time, but it will be difficult, I think. Or I optimize the AI models, which this can be doable. So now, how to optimize AI energy? Well, there are a lot of compression methods. So here I just give quick names about a lot of compression methods. And the key thing to optimize AI energy is actually to combine a lot of compression methods together. I insist on combining because sometimes people start with just applying a single compression method. But if you want to get all the benefits, you need to combine all of them to get the best gains. And so let's take again the example of flux context. And we can apply, actually, let's say, 4 compression methods. And we can start, for example, with quantization. So as we've seen before, energy is consumed via memory movement and compute. And what we can do is actually apply quantization, which will optimize for this. And in theory, what does quantization is that you move you change basically matrices which are encoded in high precision, let's say 16 or 32 bits, and you convert them to a matrix which are encoded in lower number of bits. So let's say 4 bits or 8 bits or something like this. And here, for example, it's just a simple example of linear quantization where you downscale each of the value of the matrix and then round it to the nearest integer. And this integer can be encoded in less bits. How does it impact energy? So it impacts energy because now, instead of moving a matrix with a very high precision with a lot of data, you can move it with very low precision, so with less data, so it will be faster. But also, if you do it correctly and also do quantization of the activations, you will be able as well to save compute. So in practice, how you can run this, basically, we have a package called Pruna that actually allows to do it in just a couple of lines of codes. So basically, you just specify, OK, I want to, for example, quantize it in 8 bits. And this is what we do here in floating point 8 bits. And then it takes just seconds to apply. So that's quite easy to do. And something to keep in mind, there are many variations of quantization, but I don't dive deep into the details here, but you can think of different ways to quantize the models, and happy to discuss it later. Another technique that you can apply is actually called caching. And again, this optimizes energy, memory movement, and compute. And in theory, what does caching is basically when you do a standard call to your model to generate one image, usually do a lot of steps like this, where you denoise slowly the image to slowly get the image of a car. But what you can observe is that the output of these different steps will be very similar from one step to the other. So what you can do sometimes is just cache the output of a single step and just use it for the next step. So just cache the computation so that you don't have to redo it again. And this can save a lot of computation. So again, what you can do in practice is just add a configuration and to apply caching at the same time. There are again many variations, so you can ask yourself many questions like, what should you cache? When should you cache? How you should reuse the cache later? So these are, there are a lot of different techniques to do this. Another technique that you can apply is actually compilation. Again, you can save memory and compute. And the idea is a model is usually a list of instructions, or rather a graph of instructions. And here you can see, for example, you have 4 instructions executed one after the other. And each of these instructions, they incur some memory movement and compute. And what you can do with compilation is first capture the graph, so capture these 4 instructions, and then optimize it. So optimize it would be, for example, change the instructions to have instructions which are more efficient, or just fuse them together in a single one, which then needs less memory movement or less compute. And one very important example of this is actually flash attention, which is like an attention kernel. And you might have seen this maybe sometimes, okay, I can use flash attention. And this actually increases a lot like the efficiency of your model. So in practice, what you can do is also add simply like a few lines of code to say, okay, I want to optimize the model. Again, it takes seconds. And there are many variations. Some variations might depend, for example, on your hardware or your model. Then the different compilation, you might prefer different compilations. So what kernel to fuse, what kernel to use, and so on. And the last method is actually factorization. So again, you can save memory and compute. And factorization is the key idea is basically to usually you have some matrix with a given shapes which are large, and what you can do is actually either try to do less matrix multiplication with kind of larger shapes, or do more matrix multiplication but with smaller shapes. So for example, one example is instead of doing 2 matrix multiplication, you can do like fuse the matrix operation to just do 1 multiplication with a larger matrix. Another way to do it is to approximate matrix multiplication of one of the purple matrix with the red matrix with like the multiplication of the purple matrix with 2 smaller matrices. So in practice, again, the same thing as usual. You can just add 1 line of code, take seconds, and yes, they are all, again, I cannot dive deeper in the literature for each of them, but there are, again, like a lot of variations of this. So one thing which is important is here in the snippet of code that I've shown here, I never just use a single one, so I just stacked the optimization one on the other. And so now we can see, okay, can check how much energy we have for a single model that have been compressed with these 4 optimizations. So actually, instead of 14.54 seconds that you got for the base model, you can get 1.8 seconds on H100. And that's a big improvement in terms of time, but also in terms of like of energy. So instead of like 280 kilowatt hour, you have like just 35 kilowatt hour to generate like 100 images. So it's still 63 half marathons, so still have to run, but that's better. So it represents like 8 times energy savings, which is quite huge. So one thing which is important is that beyond optimizing energy, it's also unlock kind of new use cases like near real-time image editing. So here you can see, for example, the picture of a house, and you have 2 solutions. Either you use the base model and then you edit the image just once and you burn energy for a bit nothing, or you generate 8 images and then you can generate like 8 variations of the house for the 4 seasons. I don't know, with mountain backgrounds, whatever. Yeah, I had a bit of fun to generate these images, but yeah. So here we've seen this only for like a single model, but we can check this also for like one AI inference provider. Note that there are many inference providers, like there are probably hundreds of inference providers, and there are probably thousands, even more, of AI models. But here we focus just on like the 15 latest image video AI models. And what we can do is actually estimate how much energy you would need if you just run all these models. If you check how many times these models have been run on these inference providers and how much time each of these calls will take. So you get some estimation of how much energy it would require. And what we've done actually is we optimize all these endpoints to get like more optimized models. So again, you have like new inference time and you get new estimates of the energy consumption. And actually, what we do here is when we optimize the models, we have ×2 to ×8 like efficiency, like speedups. And if we look at the total gains, in average, basically it would represent kind of ×5 energy savings. So just to look a bit more into the details, for example, only for energy, if you pay only for the energy, not the GPU rent, you would save like $140K just by using the optimized models. In terms of CO2 consumption, if you just use the optimized models, you would save, it would represent approximately 111 people spending 2 tons of CO2 per year, as recommended as to stay below 2 degree increase for global warming, to avoid global warming. And maybe the most important for your use case is actually the compute hours, which instead of 1 million, you have like 200,000 compute hours, which means that it's less compute, but also less waiting time for the end users. And these savings actually represent 91 years of waiting time for the users, which is a lot. So here in the end, the key message is that you can optimize AI energy. And of course, we have 2 options. Either you can use like endpoints from that we optimized on different AI inference providers. So we have like video, image, text, audio, and many other with many models. Or you can also want to do it yourself, learn how to do it, and just compress and deploy your own AI models. So for this, we provide like a package to do it and play with this. We provide also materials with a lot of papers. You want to dive deeper in each of these methods, but also a course with like slides and details to understand a bit more like how things work. So of course, you are welcome if you can start one of these repos. I think it means a lot for us, so it's a nice support. And yeah, thanks a lot.